When several objects are connected by ropes or strings, which free body diagram should you draw first? Sometimes none of them. These problems can look complicated because there's multiple objects, multiple forces, and sometimes multiple tension forces. Most students know what an ideal rope tells us about tension. The tension force on one object has the same magnitude as the tension force on the other object. But there's another important thing the rope tells us about their motion. When objects are connected by a rope, their motion is linked or synchronized. They move together, their speed is the same, and the magnitude of their acceleration is also the same. So instead of treating every object separately, we can treat them as one system. And once we do that, the tension between the objects becomes an internal force. So it disappears from our system free body diagram. We don't need to include it in our net force equation. And that's what makes these problems much simpler. Let's see how it works. Let's look at this example. A camp counselor is moving 3 loaded wagons across a smooth field. The 3 wagons are connected by 2 light ropes. The counselor pulls the front wagon with a 50 Newton force at an angle of 25 degrees above the horizontal. We are asked to find the acceleration of the 3 wagon system and the tension in each connecting rope. This is a very typical problem with multiple objects connected by ropes. It's easy to see that when we pull the first wagon, the 3 wagons move together and have the same acceleration. So since we are interested in their common acceleration, we can treat all 3 wagons as one system. Now look at the 2 ropes connecting the wagons. Each rope pulls on the 2 wagons it connects, but all wagons are inside our system. So these tension forces are internal forces. When we analyze the whole system, we don't need to worry about them. Remember the rule from our previous video. In a free body diagram, we only draw external forces. So let's use the same approach we used before. What is interacting with our system? First, there's the long-range interaction, the gravity. Then let's look for contact interactions. The counselor is pulling the wagon, so there's an applied force acting on the system. The wagons are in contact with the ground, so the ground exerts a normal force on the system. And that's it. There are no other external interactions we need to consider. So our system free body diagram contains just 3 external forces: gravity, the applied force, and the normal force. Once we have the free body diagram, let's set up the coordinate system. Since the wagons accelerate horizontally, let's take the horizontal direction as our x-axis, and the vertical direction as our y-axis. Now look at the applied force. This 50 Newton applied force is not horizontal, so we need to decompose it into its x and y components. To decompose the applied force, we can draw a right angle triangle like this. The applied force is the hypotenuse, and the horizontal component is the adjacent side. So Fa in the x direction equals 50 multiplied by cosine 25 degrees. And this gives us 45.1 Newton. And the vertical component is the opposite side. So Fay equals 50 multiplied by sine 25 degrees. And this gives us 21.1 Newton. In the y direction, all the forces are balanced because there's no acceleration in this direction. For our acceleration, what we really care about is the net force in the x direction. And the only external force contributing to the x direction is the horizontal component of the applied force. So we have the net force in the x direction equals the horizontal component of the applied force. Now we can apply the Newton's second law in the x direction. The net force of the system equals the mass of the system multiplied by its acceleration. So it equals Fax. The total mass of the system is 10 plus 14 plus 8 kilograms. And then multiplied by the acceleration, it equals to Fax is 45.1 Newton. And this gives us A equals 1.42 meter per second squared. And that's it. This is the acceleration of the wagons. And that's the advantage of the system approach. 3 wagons have become one dynamic problem with one net force, one total mass, and one acceleration. Now imagine that instead, we isolate all 3 wagons separately. For the first wagon, we have one tension. For the second wagon, we have 2 tensions. And for the third one, we have another tension. We'd end up with several equations and 2 unknown tensions. We could solve it, but we don't need to. By choosing the 3 wagons as one system, the internal tensions cancel out of the picture automatically. But what if the problem actually asks for the tension in the ropes? Our system free body diagram doesn't give us the tension directly, because the tension is an internal force within the system. But now that we know the acceleration, we can zoom in and isolate the wagon individually to find the tension much more easily. Let's start with the last one, since the free body diagram is the simplest. We have the gravitational force downward, the normal force upward, and the tension pulling the wagon forward. In the vertical direction, there's no acceleration, so the normal force and gravity are balanced. That leaves only the horizontal direction. The only horizontal force acting on the wagon is T. So the net force in the horizontal direction equals T. Using Newton's second law, the net force in horizontal direction equals the mass of the wagon multiplied by its acceleration. The mass of the wagon is 8 kilograms, and we already know the acceleration is 1.42 meters per second squared. So this gives us the tension of this rail rope, T equals 11.4 Newton. So this is the tension for the rail rope. Now let's move to the middle wagon. Again, let's focus only on the horizontal direction, since the vertical forces are balanced. There are 2 horizontal forces acting on this wagon. The front rope pulls it forward. We already used T for the tension in the rear rope. Let's call this tension in the front rope T prime. And the rear rope pulls it backwards with T. So the net force in the x direction equals T prime minus T. Using Newton's second law, F net in the x direction equals the mass of the second wagon, m2, multiplied by its acceleration a. And this equals T prime minus T. The mass of the middle wagon is 14 kilograms. The acceleration is again 1.42 meters per second. T prime is what we are looking for, minus, we already know T is 11.4 Newton. So this gives us T prime equals 31.3 Newton. So this is the tension for the front rope. So now we have both tensions. The rope between the first and second wagons have a tension about 31 newtons. And the rope between the second and third wagons has a tension of about 11 newtons. Notice the strategy we used. First, we treated all 3 wagons as one system to find acceleration. Then once we knew the acceleration, we zoomed in on individual wagons to find the internal forces. That's often the easiest way to solve connected objects problems. We use the system to find the acceleration, and then an individual object to find the tension. Now let's try something a little more interesting. This time, the two objects aren't even moving in the same direction. Block A has a mass of 5 kilograms and hangs vertically. Block B has a mass of 2 kilograms and sits on a frictionless incline at 28 degrees. They are connected by a light string that passes over a frictionless pulley. We are asked to find the acceleration of the two blocks and the tension in the string. At first, this looks very different from our wagon problem. If block A moves down, block B moves up the incline. And if block A moves up, block B moves down the incline. So clearly, the two blocks are not moving in the same direction, but their motion is still linked by the string. If A moves a certain distance, B moves the same distance along the incline. So they have the same speed and the same acceleration magnitude. If we mentally straighten the string, this becomes much easier to see. The two blocks still move together along the string, either one way or the other. And that means we can still treat them as one system to find the acceleration. Now, remember what we did in the wagon problem. We found the net force along the direction of motion and then divided by the total mass of the system. We're going to do the same thing here. This time, we'll treat block A and block B together as one system. So let's find the external forces acting on this system. On block A side, gravity pulls straight down. It equals the mass of the block A multiplied by the gravitational acceleration. MA is 5 kilograms. The gravitational acceleration is 9.8. So FGA is 49 Newton. On the block B side, gravity also pulls downward. But block B moves along the incline, so we only need the component of its weight along the motion direction. Now if we draw a right angle triangle like this angle is 28 degrees, and the component along the incline is the opposite side. So it equals the mass of block B multiplied by gravitational acceleration and then multiplied by sine 28 degrees. The mass of block B is 2 kilograms multiplied by 9.8. Sine 28 degrees is 0.47. This gives us 9.2 Newton. The normal force is perpendicular to the incline. It balances the component of gravity perpendicular to the incline, so it doesn't affect the motion along the string. Now compare the two sides. It's almost like a tug of war. On the block A side, gravity pulls one way with 49 Newton. On the block B side, the component of gravity along the incline pulls the other way with about 9.2 newtons. Since the force on the block A side is greater, the system accelerates in that direction. So block A moves down, and block B moves up the incline. The net force of the system is 49 Newton minus 9.2 Newton. This gives us 39.8 Newton. Now apply the Newton's second law to the whole system. The net force is the mass multiplied by the acceleration of the system. The total mass is 5 kilograms for block A plus 2 kilograms for block B. Then multiplied by the acceleration equals 39.8 Newton. And this gives us the acceleration equals 5.7 meters per second squared. But once again, the question also asks for the tension in the string. The system free body diagram helped us find the acceleration, but it didn't give us the tension directly. So now let's zoom in and isolate one block. Let's use block A since its free body diagram is very simple. There are only two forces acting on it: gravity downward and tension upward. Taking downward as the positive direction, the net force is the gravitational force, minus the tension. Using Newton's second law, the net force is the mass of the block multiplied by its acceleration. The gravitational force is the mass of the block multiplied by the gravitational acceleration. Now we isolate P. It equals mass times gravitational acceleration minus mass times acceleration of the motion. Substituting the values, it equals the mass of block A is 5 kilograms, G is 9.8, minus, again, the mass is 5 kilograms, and A is 5.7 meters per second squared. This gives us a tension of 20.5 Newton. So here's the strategy I want you to remember. When several objects are connected and move together, ask yourself, can I treat them as one system? If you are looking for the acceleration, the system approach can eliminate the internal tension forces and make the problem much simpler. If you need the tension, then isolate one of the objects and use its individual free body diagram. So remember, system for acceleration, individual object for tension. And before you start writing equations, always ask, what should my system be?